This is the second video on robot mechanics and deals with robot kinematics with a focus on mobile robotics. Let's compare robotic arm and mobile robot in terms of their kinematic. The classic zero robot arm consists of a base with the base coordinate system L0 and the links L1 to L6. On the last link is the tool coordinate system and the tool center point. The links are connected by the joints Q1 to Q6. The term Q is used to denote generalized robot coordinates, which can be either rotary joints or linear axes. The position and orientation of the tool center point TCP in relation to the base is described here with a homogeneous transformation matrix. With a serial robot arm, I can always use the forward kinematics to precisely determine the position and orientation of the tool center point TCP from the generalized robot coordinates, in this case the joint angles. Often I can also determine the generalized robot coordinates or joint angles from the position and orientation of the tool center point using backwards kinematics. For the mobile robot, the base coordinate system L0 is defined somewhere in the working area of the mobile robot, but it is not connected to the robot. It could be in the corner of a factory building or, for outer applications, at a defined location in a country. For example, the defined location of the Swiss base is in the old observatory in Bern. However, the coordinates are not 0, 0, but 2.6 million meter by 1.2 million meter, which means that the Swiss base coordinate system is not actually in Switzerland. The position and orientation of the tool center point TCP of a mobile robot is also described with a homogeneous transformation matrix with respect to the base. However, the tool is now not attached to a kinematic chain or robot links, which is why neither forward nor backward kinematics can be calculated. Instead, it is attached to a mobile robot that can move around freely. One cannot establish a relationship between the wheel angles and the position, but only between the wheel speed and the speed of the movement. In this case, one speaks of a non-holonomic system. Let's talk about how to calculate the forward and backward kinematics of velocities. We have a translational velocity vector v of link 6 relative to link 0 and represent that in the coordinate system 0. If the velocity is described in the same coordinate system to which it refers, we can write the indices shortened. At the same time, we also have the rotational velocity vector, which also refers to the base system and can also be written in shortened form. For a compact representation, we combine the two velocity vectors into one mathematical vector. How do this depend now on the generalized robot velocities of the robot arm? To perform the forward transformation of the velocities and determine this vector, we multiply the vector of the generalized robot velocities by the so-called Jacobian matrix. To calculate the generalized robot coordinates from the velocities, we multiply them by the inverse Jacobian matrix. With this, we have learned about the forward and backward kinematics of velocities of robot arms. To get to know the Jacobian matrix in more detail, I refer to the general robot kinematics. While the forward and backward kinematics of robot arms and mobile robots differ, there are no formal differences in the transformations of the velocities. For mobile robots, the derived generalized robot coordinates are the wheel movements and the movements of any actuators on the robot. Let's talk about how to calculate the forward and backward kinematics of forces. We have a force vector F and a torque vector tau on link 6. To get a compact representation, we combine them into a mathematical vector. The torques in the robot joints, so-called generalized robot forces, are denoted by Q. To calculate the force and torque vector on TCP, we multiply the generalized robot forces by the inverse transposed Jacobian matrix, which corresponds to the forward transformation. To calculate the generalized robot forces of the robot arm, we multiply this vector by the transposed Jacobian matrix, which is the inverse transformation of the forces. Now we have also learned the forward and backward kinematics of the forces of the robot arms. As with velocities, forward and backward kinematics of forces do not differ between robot arms and mobile robots. For mobile robots, the generalized robot forces are the wheel torques and the torques on all the actuators involved. This representation shows us all the kinematic relationships of a robot arm. Forward and backward kinematics of the positions, forward and backward transformations of the velocity via multiplication with the Jacobi matrix and its inverse, and forward and backward transformation of the forces with the inverse transposed and the transposed Jacobi matrix respectively. The transformations for mobile robots are identical in principle, but as we have already seen, we cannot transform positions because we are dealing with non-holonomic bindings in mobile robots. Since we cannot calculate forward kinematics, we have to use other methods to determine positions. Usually we combine odometry with global measurement systems or with SLAM. However, we cannot calculate backward kinematics either, which is why we control in Cartesian space and transform the controller values, which are mostly velocities, into the robot coordinate system. Let us derive the necessary transformations for our mobile robot, and let's start with the forward kinematics of velocities. Psi here represents the position in space and psi dot the velocity. Psi dot is equal to the Jacobian matrix times q dot and is composed of the velocity vector v and omega z. Q dot are the velocities of the left and the right wheels. The speed in the direction of travel is the average of the two wheel speeds. Vy in the robotic system is 0 because a wheel can only roll in the rolling direction. Omega is the difference between the two wheel speeds divided by the wheel distance b. We can now factor out the velocities of the wheels, and thus we have now found the Jacobian matrix from the wheel system to the robot coordinate system. Since we want to realize the algorithm as an Eros block, we also represent it graphically as such. We now have the velocities in the robot coordinate system, but would like to have it in the global coordinate system. We have already seen that we can transform the translation velocity with the rotation matrix from the robot coordinate system to the global coordinate system. We also know that omega does not change as a result of the transformation. We graph the rotation matrix, but since omega does not change, the value can simply be passed through. If we connect the Jacobi matrix with the rotation matrix, we get the forward kinematics of the velocities of the mobile robot. To determine the position of the mobile robot, we integrate the velocity and the angular velocity over time. This procedure is called odometry. We integrate the velocity vector of the robot in the global coordinate system and thus obtain the location vector. We also integrate the rotational velocity and thus determine the orientation phi. However, we have the velocity of the robot in the robot coordinate system and therefore transform it into the global coordinate system before the odometry. In doing so, we use the orientation phi determined by the odometry as the angle. We connect with the Jacobic transformation and now finally get the odometry of our robot, which gives us the velocity vector, the location vector, the rotation speed and the orientation. If we want, we could also realize this as a subsystem in Eros. We have previously assumed, without making much a point of it, that the robot coordinate system lies between the wheels of the mobile robot. This is indeed the most common assumption. But if, for example, we want to grasp something with our gripper, it is more appropriate to define a TCP at the grasping point to which we give the coordinate system t. At this point, the velocity vector is no longer restricted by the rolling behavior of the wheels and can reach any value in any direction. To calculate this velocity, we need some relative kinematics. The vt vector is equal to the velocity vector of the robot vr plus the cross product between omega r and the connecting vector between the coordinate systems system r and t. We choose an appropriate coordinate system for our calculations, and that would be r. The x components of the velocity vectors vr and vt are identical. The y component of the TCP velocity is omega times L, since y is 0 in the R system. In the graphical representation we see that Vx is not affected, as is omega. Y, however, is increased by omega times L. What we have worked out here is the Jacobian transformation from the R to the T system. We can factor out again and thereby obtain the Jacobian matrix. We can now put together everything we have worked out. With the first Jacobian transformation, we determine the velocity in the robot coordinate system from the wheel movements. With the second Jacobian transformation, we calculate the velocity and angular velocity in the TCP. Since we have determined the TCP velocity in the R system, we can transform it with the rotation matrix into the global coordinate system, where we can calculate the position and orientation of the TCP with odometry. For the inverse kinematics of velocities, we start from our equations of the forward kinematics. Obviously, we would have to rearrange the equation, and if we then multiply the velocity vector and the rotational speed by the inverse Jacobian matrix, we get the wheel speeds. This is our Jacobian matrix from the forward kinematics. We now want to invert this, but this fails because the matrix is not square. If we look more closely at the equation of the forward kinematics, we see that we actually know that y is 0 and this row can be deleted. With this, we now get a quadratic Jacobian matrix. The inverse Jacobian matrix often becomes very complex when it is inverted algebraically. For this reason, the inverse is often derived kinematically in robotics. We start from the same relative kinematic equation that we have used before. If we use it to calculate the velocities of the wheels, the velocity of the left wheel is reduced by omega multiplied by b half and increased by the same amount for the right wheel. With this, we find the equation for calculating the wheel speed and thus the inverse Jacobian matrix. Sometimes you can also calculate the inverse with a computer algebra program, as I did here with Wolfram Alpha. Often the transformation is clearer if instead of speaking of the inverse of the Jacobian matrix from W to R, one simply speaks of the Jacobian matrix from R to W. As we have seen, odometry replaces the forward kinematics of position and orientation. But this alone is not enough, because the value estimated with odometry is inaccurate and drifts away. Therefore, odometry is combined with global sensors or with measuring systems that have no drift. The inverse kinematics of the positions also does not exist. This is replaced by a controller that controls the robot on a path in the global coordinate system and has velocities as control value set point, which can then be converted into target wheel speeds. Let's calculate the inverse kinematics of the velocities when we start from the TCP. The velocity in the direction of travel and omega are identical in the TCP and the robot system. With the relative kinematic equation, I can now determine y and visualize the whole transformation graphically. Since the forward kinematic is quadratic, I can also determine the inverse. However, The solution I found has a velocity orthogonal to the direction of travel of the wheels in the robot coordinate system, which is why it only makes sense if I use omnidirectional drive. But if I have wheels, VRY must be 0 in the robot coordinate system. From this constraint, I can determine the rotational speed omega, which is now no longer freely selectable. With this, I can now make a new graphical representation of the algorithm, which now has the applied velocity vector as an input variable, but only the driving velocity and rotational velocity omega as an output variable. This reduces my Jacobian matrix and its inverse. Thus, we have found the solutions listed here for the inverse Jacobian transformation from the TCP. If we summarize the forward and backward kinematics of the relevant transformations between the global coordinate systems and the TCP coordinate system, we find the following. With the forward kinematics, that is odometry, we calculate the position and orientation of the robot from the wheel movements. We need this as an actual value for the Cartesian position control in the global coordinate system. With the inverse kinematics, we calculate the necessary wheel speeds from the global movement requirements. With the rotation matrix, we calculate the velocity vector of the TCP in the robot coordinate system from a given velocity vector of the TCP in the global coordinate system. With the first Jacobi transformation, we calculate from this the driving and rotation speed of the robot, and with another Jacobi transformation, we finally determine the target speeds of the wheels. It is interesting that with this concept we can move the TCP omnidirectionally. For inverse kinematics, however, we need the angle from the forward kinematics. We have found the following Jacobi transformations. Transformation from wheel system to robot coordinate system. Transformation from robot coordinate system to TCP coordinate system. Transformation from robot coordinate system to wheel system. Transformation of velocity vector and rotation speed from TCP system to robot coordinate system for omnidirectional robots. Transformation of velocity vector from the TCP system as a travel speed and rotation speed into the robot coordinate system. That was the introduction to robot kinematics and our overview of the most important kinematic calculations for our mobile robot. We did not look more closely at the transformations of the forces for our mobile robot because they are rarely used in mobile robotics. However, I find force control in omnidirectional robots very useful and would like to add this at a later date. We are happy to answer questions about this on the forum on Moodle at online.robotics.ch. Thank you for your interest, and we look forward to welcoming you to the next video on robot dynamics.